Okay, I would like to continue from the topic for inheritance. So today, I would like to try to finish the slides. I'm not sure if I can, but at least finish the majority of the slides about inheritance. Especially, I want to talk about polymorphism and dynamic binding. I want to repeat the intuition that we talked about last time, just to get you warm up. And then today, the main goal is I'm going to present to you a systematic rules about how you can judge if something should compile or not. That is something you're supposed to know, okay? So since we talk about design, you should really know the heart about object orientation, which is inheritance, polymorphism, and dynamic binding. And we should learn the rationale behind why things go this way. Okay, so now just before I start, I would like to remind you again, this particular syntax over here. Again, I kind of provided the Java syntax for your convenience. Let's do that one more time, okay? To make sure, otherwise you'll get lost very easily today. In Java, you assign new object variables using an assignment over here, right? That's an equal sign in Java. And then on the left-hand side, you declare variable s to be of type students. So the green one, we call it static type, which means it's declared and can never be changed. On the right-hand side, you use the new keyword to say, I'm going to create a new object. So that means that's going to happen at the runtime. So that's called dynamic type, which can be changed throughout the runtime. Okay, so now, how do you do such syntax? So you can see that in this case here, the static type and the dynamic type can be different, okay? But they are subject to certain rules you have to follow. So now, what about in IFO? So IFO, the declarations and the assignments of the new variables, they are in different lines, okay? They're separate. So now, when you declare, you say S is of type students, RS is of type students, the same. Okay, so these, I'm trying to show you two blocks of code that are equivalents. And then when you say create over here, you can see I use the color red for dynamic and green for static. Over here you can see student, I say create student s.make. That means I declare s to be a student, but at this point in runtime, I'm assigning a new student object to it. So the dynamic type is also students. So in the second line over here, RS was declared as also a student class type, and now I'm assigning a resident student as the runtime object to it, okay? So again, you really want to get used to the syntax. But in terms of Java and IFO, the concept are really the same, nothing new, okay, in terms of the syntax. Just the syntax a little different. Any questions about the syntax over here? Okay. Also, in IFO, you can abbreviate the notation if you like. You can see in the case of this line over here, I say create student s.make. Remember, so s was declared of type students over here. If the green one and the red one, the static and the dynamic types are the same, you can abbreviate that, okay? This is what you can do. You can simply say s.make. You don't have to mention dynamic type anymore. That means it's simply the same. Okay, that's the syntax we have to use throughout the lecture today, okay? Okay, so now let's move on to what we did this table together, right? So you should really go over that. And let's talk about the intuition again. I want to go over the two cases once more because that's gonna help. Okay, let's now say we got S and RS. S over here was declared as student class, and RS over here is declared as resident students, okay? One is students, the other one is resident students. Remember the hierarchy we have. We got students at the top. We got two subclasses there, resident students and non-resident students. Okay, that's the inheritance hierarchy we're talking about. So now we create S to be of dynamic type, also student. That's why I abbreviated notation. And also RS, also resident students. Now we consider these two assignments over here, 8 and 9. And I asked the class last time which one should be correct and which one should be incorrect. Okay, so it turns out line number 9 is incorrect, negative, whereas line number 8 is correct. Okay, that's something we really had to think why, because you don't just want to memorize. Okay, let's think about why. Okay, let me actually try to draw some diagram again. Okay, it's really important to get an insight. Okay, over here at the page below. Okay. So now let's do it again. We say that S is of type students over here, and RS is of type resident student, I'll say RS for short. And now this is the declaration. First of all, we have to understand what does it really mean when we declare S to be a student. Okay, what does that mean? Over here, let me just use a different color here. When I say this line over here, it already constrains what features I can call on this particular variable, okay? So this, okay, I already have here, a variables static, a variables declared type constrains what features you can call. You can call upon that. In this case, what features do we have? Let me just remind you very quickly about the hierarchy we have. So we have students, and we have resident students, and we have non-resident students. In the student class, we have the common attributes, right? We got names, we got courses, and we have register, and we have tuition. So these are the features of the student class. So they're all inherited to the subclasses. And what about resident students? For resident students, we actually got only one new feature, which is called premium rates. So I'll say PR for short. And for NRS, we got discount rate. And also you have set premium rates. Also you have set discount rate. So that's kind of the setup. So now, over here, what can we call on S? This question here. In this case, the only features you can call would be only over here. For example, you cannot say the following. You cannot say S dot PR. That would not be okay. If you say S dot DR, that's also not okay. They're too specific. Okay? So only the static type, only the declared type determines what features you can call on the variable. Okay? Having this in mind, we'll try to prove why one assignment is valid, the other one is not valid. Any question up to now? That's really important. You can see so far I haven't talked about anything about runtime types. It's simply because the features you can call only is determined by the static type. Okay? Nothing else. Okay, let's now consider this line of code over here. So now let me say the following. If I say creates, let me write it in full detail. Creates students over here, and then S dot make. And I will say S over here, and also creates resident students, RS dot make. And then I'll say RS. Okay? So I've created two objects now, so we do have some runtime type. So now let's visualize this quickly. So we got two variables. S is pointing to some students objects. I'll draw the contents of the object in just a moment. And also we have RS is pointing to over here, resident students. Okay, that's what we have. So what should be the contents for students? In that case, we should only get names and courses, only these two attributes. Name and I'll say CS for courses, only that. What about RS objects? Does it have more attribute, right? It has also premium rates. For RS, we got three attributes actually. So the name and courses, they are inherited from the student class. And also we have the premium rates. That's something that's extra. Because that's extra, I'm gonna highlight that. That's something that's more in the subclass. Okay? So now let's consider the two assignments we have. So let's say we have, let's just try to consider the one that's wrong. Okay? That's not allowed. RS is assigned to S. Okay? First of all, this one here simply does not compile. Simply does not compile. But how do we see why it does not compile? Okay, let's prove by contradiction. Proof by contradiction means I assume something that's actually true, and that will eventually lead to something that's contradictory. So that means my original assumption should be false, right? That's proof by contradiction. So let me say step number 1. If Rs is assigned to S was allowed. Okay, let's say we assume that. Eventually I'm going to lead to some contradiction. So now I'm going to do, let's do a little bit similar exercise. Remember I said before, what can we call on S? That's going to be S. We know that S.PR is not possible. Also S.DR is not possible. Let me ask a similar question to you. So what can we call, let me use a different color here. What can we call on RS? What can we do? Can we say RS.name? We can, right? That's defined, actually inherited from the student class. Can we call rs.pr? Yes, okay, that's really important. When we say rs.pr, this one is okay. That's really critical, okay? So which means part of the expectation for rs, which was declared as resident students, means we can say premium rates. Can we say rs.dr? No, right? Because it's a separate class, okay? rs.dr is not part of the expectation. Again, when you talk about expectation, that's static type, it's declared type. Okay, having this in mind. Now, step number 2. We know that rs.pr should be allowed, should be possible. Okay, that's something we just discussed. And let's now try to think about what this assignment over here really means. When I say RS is assigned to S, what does that mean? Because RS and S, they're reference variables, which means they store addresses of objects. When I say RS is assigned to S, I'm copying the address that is stored in S into RS, right? So how should I change the diagram? In this case, what I'm really doing over here is, so now RS is not going to point to here anymore. It is going to point to wherever S is pointing to. That's what RS assigned to S means. Any questions up to now? Okay, we're getting there, okay? So now, here's the thing. We know that rs.pr should be possible. After the assignment over here, rs is actually pointing to a student object. What's going to happen if I say rs.pr? PR is actually not available in a student object, right? Because student object does not declare any attributes called PR. So in this case, if we allow such thing to happen, that means crash. Because there's simply no such thing at the runtime, so you just crash or some exception happened. So this is the contradiction. So we can go back to our original assumption there. So since we got crash over here, so that means over here, so this means this should not be allowed. RS is assigned to S, not allowed. Okay, anybody follow? Anybody not follow, actually? Anyone who's not following? Okay, if you follow this, okay, very good. So this explains that whenever you're trying to put something on the right-hand side, it has to be a subclass, basically. Okay, maybe that's how you memorize the rule before, but it's really critical to understand why it is the case. Okay, yeah.
How would you make this valid then? Like, if you change RS as when you're doing the static, to make it a student, would this be valid?
Yeah, there's a good question here. So the question was, in the current setup, how can we make it work? Well, one way to make it work is I can change the temporarily. I'm going to undo this, or just for now. I can say now RS rather than RS. I can say just students. That will be okay. Okay. But I would say hold your question a little bit because we are still just talking about some example here. I'm going to give you the precise systematic rules you can follow. Okay. Let me just undo this to avoid confusion. Okay, guys, if you have no question, I'm going to move on. Okay? So if you go back to the slides, you will see that for the intuition, I actually explained to you why one thing is valid, but the other one is not valid. So I will leave the valid case for you. That one is also very quite similarly proved. Okay, I'll leave that to you. Okay, the polymorphism, I would say this one is that's the trickiest one to understand. Dynamic binding hopefully is better. Okay. Okay, let's now talk about dynamic binding. That's where we should start from today. Okay. Let's say we have one variable called course, C, and also students. Now the static type is just S, right? Which means we can call names, courses, tuition, not premium rates, and not discount rate. Okay. Let's say we create a course 3311 over here. And now let's say we have some resident students over here. And then, so which means now RS is pointing to a resident students. We have another line here. We have NRS. So NRS is pointing to a non-resident students. Okay. So now the question is, let's say we set the premium rate and we set the discount rate for RS and NRS. Okay. So now, let's say I do the following assignment. If I say S is assigned to RS, I can tell you that this is valid. We are assigning something that's more specific, like resident students, into students. Okay, this is valid. After this line here, can you be convinced that the tuition we get should be 125? Okay, let's see how the diagram will change. Okay, so now let me just go back there. So resident students and non-resident. Okay, let me just draw the diagram again. Okay, that's also important to get right. Okay, let me add a new page over here. Okay, so now let me just write down also the things that are involved. S is students. RS is resident students. NRS is non-resident students. Again, these are just decorations. Okay, so now, when I say creates resident students, and I say rs.make. Okay, I'll just say I have some name over here. Okay, what this does is it's going to have rs that is pointing to some resident students objects, which somehow has the premium rate, right? So I can set the premium rate. I can say rs.set premium rates. It's a 1.25. Okay, so which means the premium rate over here is 1.25 for RS. Okay, let me do one more. Let's say we also get C also of type course. And also you can say creates C.make. Okay, I can say 3311. Let me be consistent with the slides. I said over there 100. Okay, 100. Which means we have a course object over here, and its title and fee, 3311 and then $100. Okay, and now what we can say rs.register C. So that means somehow the courses over here, part of it is going to be this course over here, part of it, just conceptually. Okay. Okay, now let's create another one. That's section 1 and also section 2. We say creates NRS dot make some name over here, NRS dot set discount rate. And now in this case 0.75. And let's, sorry, no semicolon. And then NRS dot register. The same course, let's say. Okay, let's complete the diagram and then we'll be ready to consider dynamic binding. Okay, so now let's say we got NRS over here, which is just another kind of object, NRS, and we have discount rate, which is 0.75. And then we also got courses over here, and they just happens to be classmates. Okay, now we are ready. Let me use a different color. After this, let's say the following. If I say S is assigned to RS, and then I say S dot tuition, what should that be? Let's just do the assignment first of all on the diagram. First of all, S is a student's variable. So we can assign a resident student to it. So now S, after this assignment here, is going to point to RS. So we say that the static type of S is always students. It doesn't change. It remains to be students. But now the dynamic type is now RS. So what should be the tuition in this case? It should be 100 times 1.25, which is 125. Okay, that's what this line would do. So depending on which student object you're pointing to, it's going to apply different rates in order to calculate the tuition. In this case, because S is pointing to resident students, so that's why you're calculating according to the premium rates. Okay, let's do another line to clarify this stuff. If I say S is assigned to NRS, okay, we know that S is not going to point to here anymore. It is going to point to this non-resident student object. Now, it's pointing to a different kind of object which supports a different kind of rate. In this case, it's going to be the discount rate, 0.75. So now, if I call the following, if I say S dot tuition, so now what should that be? Should be 100 times 0.75, which is 75, right? You can see in both cases, let me just highlight the difference over here. In both cases, we are trying to say S dot tuition, but depending on which object is being pointed to by S, it's going to calculate differently. So we say the object that's being pointed to is called dynamic type. Okay? It's called dynamic binding. Again, it's only intuition, okay, just to give you some understanding. And then we're going to see the systematic rules. Okay? Guys, any questions? Anything unclear? Please ask. No? Okay? Okay, if this is okay, you can follow the slides. That's exactly what I just illustrated. You can just follow that. You can also see the diagram there. Okay? Okay, so now I want to talk about the systematic rules. So we're going to go through a little bit like a theory, but it's not really completely mathematical. It's not really. But we're just going to define some terms properly. Okay? I'll come back to this inheritance hierarchy a little bit later. It's about smartphone. I'll come to this when we talk about examples. Okay. Okay, let's go through some slides over here, and then we'll get to the rules. So now, what is a type? A type is talking about the related values that you can have at the runtime. So a type is simply a set of related runtime values. And so each class we declare, they can be instantiated into different objects at the runtime. So a class can be used as a type. Let's say person can be a type. That means at the runtime you can have different addresses for the person objects, right? So it can be a type. So now, that's the most critical part. So once you have the inheritance, either using the inherit keyword in IFO or extends in Java, you form a hierarchy of your classes, right? And we have to define some terms over here before we can define how the rules should be. First of all, the implicit root of the hierarchy is any. So we talk about a tree, basically. So what you learned from 2011, a general tree. Okay. And then, so let's now try to define some terms. Each inherit declaration, yes, if I say class A inherits class B, so we do have some upward arrow. So let me just draw some diagram here, just to illustrate. Let me just use this diagram here to illustrate. Okay, let's say we have this. Let's say we have class A, which inherits class B. And also we have class C also inherits class B, right? So each up arrow means an inherits. And also class B inherits class D. Let's say we also got another class E over here, and we have F over here. Okay, that'll be enough. Let's say this is the hierarchy we have. So E inherits A, F inherits A inherits B, okay, etc. Okay. Let's define some term. Let's say we talk about from A's perspective. We're going to define two terminology, two. One is called ancestor. Ancestor simply means, oh, by the way, just one more thing. When I say A inherits B, and also B inherits D, so this means something, this is something called transitivity. So that means implicitly A also inherits from D, implicitly. Okay, so you can, of course, this relation can keep going. So it's like A less than B, B less than C, so A must be less than C, right? A inherits from B, and B inherits from D. So A implicitly inherits from D. Okay, that's what we have. So now let's define this term here called ancestors. So what's ancestor? Basically, any class that A either explicitly or implicitly inherits are the ancestors of A. In this case, what do we have? Ancestors for A. B and D, okay, very good. But our definition for ancestor is a little bit, we got a little bit special. A class is also the ancestor of itself. So now the ancestor for A is going to be A itself, B, and D, all the way down to the root, up to the root, okay? So the ancestor of A will be itself, B, and D. So this will make our assignment rule much easier. Okay, that's ancestor. So what about descendants? That's another thing. Descendants. It's actually the opposite direction. Yes, exactly. So, which means a class is both its ancestor and descendants for our definition. Okay. So now, how do we define descendants? It's the opposite direction. Any class that either directly or indirectly inherits A, they are A's descendants. Okay, you will see the definition there. In this case, what will be the descendants? AEF, thank you. Okay, descendant over here, there'll be A itself, E, and F. Okay, those are the descendants. Okay, A, E, and F. Okay, let me just illustrate a little bit more points over here before I go back to the slides. Let's say over here, let's make it some naive illustration here. Let's say in class D, we have a feature called D, little d. In class B, we also have a feature called B, little b. And A here, we have E here, F here, and little c here. Okay? So now, over here, if I talk about A, do you think A contains more code than its ancestor? Strictly more, would you agree? Because A inherits everything from its ancestor. So even though we only say A over here, so A actually contains also B and D. Agree? So which means the lower the hierarchy, the more code you will accumulate from your ancestor. Okay? That's really important to note. Okay? That's basically related to our intuition because in some way the resident student has more code than the students, right? Okay, that's something I want to say. Any questions until now before I move on? Okay. And then we're getting to the actual meat. So that's about ancestor and also the descendants. Okay, so now try to understand this. A inherits all the features from its ancestor classes, right? We just illustrated that. So what's the consequence of that? That means any instance of A, so they have a wider range of expected usages. What do I mean? I'll show you exactly like this. Let's say over here, I'm going to use a different color here. Let's say we have some, let's say we declare object D of type D, object B of type B. We got object A of type A. So now let's think about expectation. Expectation. Now let's, over here. So let's first put the objects variable over here. Okay, I'll put it here, and also expectation. So we talk about OD, OB, and OA. What's the expectation for OD? Just D, right? Because that's kind of at the top over there. So you can only say OD dot D. Because D was declared of type D, so you can only call the feature over there. That's it. What's the expectation for OB? B and D, right? So that's actually wider expectation. That's what I meant from the slide. So that'll be, you can say OB dot B, OB dot D. Okay, it's actually B and also D. OA, OA dot A, OA dot B, OA dot D, right? OA dot A, OA dot B, OA dot D. So the lower you are in the inheritance hierarchy, the more code you have. That means we can expect more from you. Okay? That's really the critical insight into the inheritance. Okay? And based on this, we're going to have the rules for assignments. Okay, let's go back. Okay, I think just a little bit more points about here. Okay, the lower a class is in the hierarchy, the more code it has. It accumulates from the ancestor classes. Okay. Okay, so in any descending class, this is what you can define new attributes, you can define new queries or commands, or you can redefine your features, right? That's what you can do. Okay, that's not really difficult. So now here comes the critical points. Let's see over here. When expecting an object of a particular class, we may substitute it with an object of any of its descendant classes. Okay, now what do we really mean? Okay, let me just make it an example to you. First of all, let's say we are expecting a students. So what do we expect from the student? We can say students.name, student.courses, and also student.tuition. That's what we can expect from the students. In this case, what can I substitute as student for you? I can either give you a resident students or non-resident students. I just give you more specialized objects because they're guaranteed to support the name, courses, and tuition. Right? Okay. Now, let me just use the diagram there to show you. Okay. Again, we have students. We have resident students, non-resident students. Okay, over here we have name, courses, tuition. Here we got premium rates. Here we got discount rate. Okay, so now let's say over here, if I have S of type students. So now what can we expect from the student? We know that should be name, courses, and also tuition. So these are our expectation. So now, what can I give for this particular student variable? What can it point to? So now, S may point to a resident students objects. That will be okay, right? Or S can be pointing to another non-resident student objects. That'll be okay. Okay? Why? It's simply because resident students over here is a descendant class of students over here, and students over here, right? So that's how you judge the rule. Guys, are you following or lost? Following, maybe? Okay. So, okay. Maybe what I will try to do today, I'll try to go as many slides as possible. You should really study over the weekend. I'll give you some exercise to do, so you can see what I will expect from you in the lab test. How about that? You need some pressure, I guess. Okay. Okay. Now let's just see this. Now let me one more slide and then I'll define the rules. Okay. So this is what I mean by substitution. Okay. This one is a little bit theoretical. I'll leave that to you. This one is just about if whenever you do any assignment, V1 is assigned to V2. For example, S is assigned to RS. How do we judge if a particular assignment is valid or not? You have to see some certain rules. But I'm going to introduce you to the rules in just a moment. Okay? Okay, so now, here are the rules of substitution. Substitution simply means assignment. Okay? Let me just say one more thing to relate that to you. Okay? So what do I mean by substitution? Whenever I say, for example, S is assigned to RS, okay? So this we know that is an assignment. Okay? And now we say that we substitute RS for S. Okay? Because what this means, after this assignment here, S is going to point to wherever RS is pointing to, right? They're going to point to the same object. So we're substituting RS for S. Okay? That's what I mean by substitution. Okay. Okay. Let's see some definition here. Okay. So now, here's the rule. When you are expecting an object of class A, it would be safe to substitute it with an object of any descending classes of A, including A. Okay? Let's see an example right away. Let's say over here, if I have S students, RS resident students, NRS non-resident students. Let's now consider a different assignment over here. Let's apply the rule. Okay? When I say S is assigned to RS over here, the only thing you gotta look up to decide will be what's the static type for both sides. For S, the static type is students. It's declared over here. And what about the static type for RS? Resident students, right? The static type is resident students over here. So let's look up that first. And now here is the question. Should this assignment compile? Okay, yes or no, right? Let's ask the following question. Is the static type of RS a descending class of the static type of S? That's basically the question you're asking. Okay, let's figure that out. Okay. The static type of RS, we know that is resident students. The static type of S, we know that is students. Now the question is RS a descending class of resident students? Sorry, is RS a descending class of students? It is, because we do have the hierarchy here, right? RS is a descending class of students. So this should compile. On the other hand, if you try our original, the intuition example, if I say RS is assigned to S, I reverse the order. In this case, we ask the same question. The static type for S is students. The static type for RS is resident students. Now, is students a descending class of resident students? No. Apparently no, right? Students is not a descending class of RS. It should be the opposite. So the answer is no, so it will not compile. That's how you apply the rule. Okay? Follow? Okay? Yeah. Please, question. Yes. Yeah, exactly. So I'll give you a tip. Every time if the question is, should this line of code compile or not, only look at the static type. Only. Maybe that answers your question, I guess? Yeah, good. Only look at the static type. Yeah, go ahead.
So basically, casting is...
Are you talking about cast?
Yeah.
Let's not worry about cast for now.
Okay.
We'll get to cast a little bit later. Guys, yeah, please. No, actually here we just talk about what kind of assignment you can do, right? You can do S is assigned to RS, but not vice versa. But later on, yeah. Oh, yes. Yeah, exactly. So later on we will see that. So so we can say S is assigned to RS. You can also say S is assigned to NRS. In that case, depending on which one you're pointing to, you're going to call different versions of the tuition. Right? That's dynamic binding. Not really memory, just about the flexibility, right? Because conceptually, you're just moving from one object to the other. You're changing the type at the runtime. Depending on which type you're talking about, it's going to call different version of the feature, right? Yeah. Okay, let's move on. Okay. Okay, so now you can follow the rest. Okay, so basically this one is about when it is safe. And it will be unsafe if you try to assign something to its ancestor class objects. In that case, that will be unsafe, right? Okay. Okay, now let's again clarify static type and dynamic type. Okay, this will be more formal. A reference variable static type is what we declare that to be. For example, if you say Jim colon students, that means Jim is of static type students, never changes, never ever. Okay. Now, when you say my phone is of type smartphone, by the way, so if you look at the, I'll upload this hierarchy to you as well. So this is another class hierarchy I put out as an example for you. I'll go over that very quickly. So basically what you have is like a hierarchy like this. At the top you have smartphone, which we got different subclasses there. You might have iOS, you might have Android. That makes sense. Under iOS, you might have, this is old model, iPhone 6s, iPhone 6s Plus, right? And also under Android, it might be Samsung or HTC, you get the idea, okay? You can see for any smartphone, we have to support dial. At least you can dial the phone number. And also you have to make sure you can surf the web. So these are the generic features. So they should be supported by all the smartphones. Let's say for iOS, we actually redefine the way you surf the web. Maybe because you actually use Safari to actually surf the web. On the other hand, for the Android, you also redefine the surf web feature, maybe using Firefox, maybe. Okay? And also you have, in iOS, you have some new feature called FaceTime, which is not supported by Android. And also for Android, you support something called Skype. Let's say it's not supported by default in iOS phone. Okay, you get an idea. You can feel free to see this hierarchy here. Some example I mentioned in my slide, I can kind of refer to this hierarchy here, so you can follow. Okay, okay. Now, the static type never changes, and also the static type tells you exactly what you can expect from the variable. Okay, that's something we keep mentioning, okay, keep emphasizing. Okay, so now let's do one more. If I declare Jim to be a student, you can say Jim.register or Jim.tuition, Jim.name, Jim.courses, but you cannot say Jim.set premium rates because that's specific to resident students. You cannot say Jim.set discount rate either. That's specific to non-resident students. Okay? Okay, similar, just for the smartphone hierarchy, you can refer to that. Okay. Static type is very easy. Once you declare that, it's fixed over there. Okay? So now let's see, what about dynamic type? Dynamic type is a little bit complicated, okay? A reference variable's dynamic type is the type that it's currently pointing to at the runtime, so it can be changed. Basically, every time you do a reassignment of your reference variable, you might change its dynamic type. And there are two ways you can change it. There are two ways, okay? I'll show you both. Okay, so every time you do a reassignment, you can change it. There are two ways. Okay, first way is easy. So let's say over here, let me just show you what you can do. For example, let's say you say Jim is of static type students, is static. And now, when you say creates, and then this is the dynamic type we are assigning to Jim, right? We are assigning Jim to be a resident student's objects, right? At this point. Okay, now here's the thing. Let's say I give you these two lines of code. I say Jim is declared to be students, and also I'm trying to assign Jim dynamic type at the moment to be resident students. How do you judge that these two lines compile or not? How do you judge?
When you look at what the static type is, if the static type is an ancestor of that dynamic type, it can't become that type.
Yeah, it can, yes. So basically, yeah, that's exactly what the rule is saying. So here you can see the new objects class must be a descendant class, right? So you can see over here, resident students, that's a new type. That should be a descendant class of the static type. Okay? So we always assign something to its descendants, including itself. Okay? So guys, let me give you a tip. I wouldn't mind if you don't quite follow in the lecture, but here's the number one thing when you think about this issue. We started with the inheritance with code reuse, and we talk about code accumulation, which means every time when you create a subclass, they accumulate the code from their ancestor, which means you can expect more from them. So now, if I declare a class with certain type, I want to assign that to something else. What would be the safe way to do? I certainly can assign that particular object variable to its descendant classes or descendant objects because they're guaranteed to have at least as many code as their ancestor. Okay, that's kind of the critical thing. If you really get this clarified, I think everything else hopefully is not too bad. Okay. Yeah, go ahead. Sure, no problem. Okay, let me just make it explicit to you. Okay, sorry. Let me just go back to this node here, and then I'll add a new page. Yeah, new page will be good. Okay, let's do this. Again, let's see the context. S is students. And over here, we say that creates resident students s dot make. And be reminded that we have students at the top. And also we have resident students and we have non-resident students. Okay, that's what we have, right? Okay, let me be more explicit here. Over here, we declare S to be of static type students, green. And now, whenever you see this bracket notation over here, that means that's a dynamic type. Okay, now the question is, do these two lines compile? Do they compile? Okay, and the question is, we are trying to assign S into some resident students object. That's what we are trying to do. Okay, S was declared as students. Is this a substitution valid or not? Right? We ask the following question. Is the new dynamic type, which is RS, a descendant class of the static type of S? Is that the case or not? Right? So now you can see that what's the dynamic type over here is simply RS, right? And what's the static type? It's simply just students. So now it boils down to, is resident students a descendant class of students? In this case, yes, so it compiles. Let me give you, yeah, go ahead. Yeah. Okay, let me give you something that wouldn't compile. How about that? We just do this exercise here. Let me just do another page over here. Let's do something here. Let's say RS is of type resident students. Let's say we say that creates students rs.make. Also, we have another one, creates non-resident students rs.make. Also, we have creates rs.make. So we got three lines over here. Let's say you can write. Okay. Again, this one over here is static type. And these three are the potential dynamic type we'd like to attempt to assign. Okay? Now, which lines is going to compile? The third one, right? Okay, let's call this 1, 2, and 3. The third one is going to compile because, it's again, I will say students, RS, and we have NRS. The third one compiles because RS is a descendant class of RS. The second one does not compile because NRS is not a descendant class of RS, if you can see the hierarchy. NRS is not a descendant class of RS. They are not. They're sibling in some way, right, in the tree terminology. Finally, this one also does not compile because students over here is not a descendant class of RS. It's completely reversed. That's how you judge. Okay. Guys, any questions? Yeah. Okay, good. Okay, very good. Okay, you can go through the rest. Okay, so what we just talked about is the first way of changing the dynamic type. Okay, that one's easy because you got explicit the brackets over there for you to check. But now the second way is a little bit indirect. Okay, the second way is if you're trying to do some variable assignment, when you say variable v is assigned to other. In this case, you know, the idea is also simple. If I'm trying to say v is assigned to other, how is v's dynamic type going to change? It's simply going to change to the dynamic type of other. Okay, so what does that mean? Let's see some example here. Again, we got Jin, which is students, RS, and NRS. Again, we got 3 different static types. So now let's say we do the following. Let's say we got this, we got this, we got that. Okay, different dynamic type. At the moment, let me ask you one by one. What's the static type of RS, static type? Resident student, right? What's the dynamic type for RS? Also resident student, the red one. They happen to be the same. Okay, just check. Let's say after this, when I say RS is assigned to Jin, let's do some little bit test on you. Is this valid or not? Why not?
Because now you're removing code from the class.
Yep. But let's try to explain in a more satisfactory way, okay? Yeah. So the reason that this does not compile is because the static type of Jin, which is students, is not a descendant class of the static type of RS, which is resident student. That's why. Okay? When I give you the exercise, I also give you model solution, so you will know exactly what I expect from you. Okay? This is not good. What about NRS is assigned to Jin? The same. Okay? Static type of Jin, students, is not a descendant class of the static type NRS, which is non-resident students. Now, let's say this. If I say Jin is assigned to RS, we know that this is okay, right? Now, question here. After these assignments, what is the static type of Jin? Static type. Still the same, exactly. It never changes, still students. What about dynamic type? Before that, it was just student, before that. But what about after this? Resident student, it changes because it's going to point to the same object that RS is pointing to. So the dynamic type changes to be whatever the dynamic type of RS is. Okay? Okay, good. Now, what about when I say Jin is assigned to NRS? In this case, again, after this assignment here, what's the static type of Jin? Students, doesn't change. What about dynamic type? Non-resident students, right? Okay, you get an idea, just the second kind. So you can see that the second way is really indirect and can be very complicated because assignment is so often occurred in your code. So if you really want to keep track of, it's got to be careful, okay? That is why it's an undecidable problem in general for the computer to solve, okay? But let's not get there. Okay, let me define polymorphism and dynamic binding, and then we'll see a more interesting concept, okay? So polymorphism simply means an object variable may have multiple possible shapes. For example, a student variable, the student is a static type. How many possible shapes can it have? It can be either students, it can be a resident student, it can be a non-resident student. Basically, all the descendant classes, okay? So because of this, we have, since For this particular class, it support feature, let's say in the student class, we support the feature tuition. And the tuition feature is inherited to all the descending classes, right? Since all the descending classes can be the possible shape, that means we got different versions of the tuition. It's either the tuition in the student class where we only calculate the base amount. It can be the tuition in the resident students class where we compound that with the premium rates. It can be the third version in the non-resident students class where we try to do that with a discounted rate, right? That's exactly what's going to happen here, right? So for just by declaring S to be of type students, you got 3 possible versions at the runtime that might be called. It really depends on which runtime object it is pointing to, okay? That's polymorphism. And that's highly related to dynamic binding. Dynamic simply means it's happened at the runtime. At the runtime, if I point to a particular line of feature call, I will ask you what should be the output, right? So let's say, let me just make it again. Over here, if I say, for example, S. Oh, actually, I do have example over there. Just bear with me. I think it's in the next slide. Okay, over here. Let's say we got Jim, we got RS, we got NRS. The same example, just be consistent. So now let's say this. So we have RS and NRS. So if I say Jim is assigned to RS, and then I say Jim.tuition, just tell me which version of tuition it is going to call. Which version? The version in the student class or resident student class, right? It's simply because after this assignment over here, the dynamic type of Jim becomes resident students. It's simply because of that, okay? Okay, and then if you say Jim is assigned to NRS, now making exactly the same feature call at the runtime is going to give you different results, simply because the dynamic type of Jim changes from resident student into non-resident students, okay? Good. So now I also included, by the way, the sample code has been updated. You can certainly play around with the code. All the code is available. You can play with it. Okay, so now this one, basically we said it already, so this one you can just go over. Okay, this one, no surprise. Okay, you can see that so when we are trying to make exactly the same feature called Jim.tuition over here, and also Jim.tuition over here, exactly the same feature call, but it can give you a different result, simply because at one point it points to the resident students, at the other point it points to the non-resident students. Okay, good. Okay, any question up to now before I talk about cast? Okay, we're doing okay, we still got 20 minutes. Good, yes? Jim to RS, not RS to Jim. Let me just go back. So you mean Jim is assigned to RS like that? Yeah. Yeah. Okay.
So Jim now points to
resident students.
So can you call Jim set AR?
No, it's a very good question. Very good question. Let me clarify that. Let me write it out and now explain that. S students, RS resident students, okay, static type. And then we say creates rs.make over here. And then we say that, of course, if you say rs.set premium rates, let's say to be 1.5, this is okay, right? Now, the question was, I do the following. S is assigned to RS. And now, can I say the following? S dot set premium rates. Let's say 1.7. That's the question. Can I do this line or not? Is it going to compile? Hint, I talk about compilation. Remember what I said to you before, when you want to talk about compilation, you only judge by static type. So, tell me.
The static class does not have that.
Does not have that method, right? Okay, so now, actually that's actually is a very good question for us to introduce casting. Okay, so now let me tell you, let's see what's going to happen here. 1, 2, 3, and 4. After 1, we have RS pointing to some RS objects. Okay, use a different color here. So now after number 2, we actually set the PR to be 1.5. Okay, now after 3, over here, S is pointing to RS. So your intuition, I'm pretty sure your intuition was, since S is pointing to a resident student's object, so we should be able to call set PR. However, IFO compiler or any other compiler, like a Java compiler, they are not that smart. They cannot really tell that even though currently S is pointing to a RS object, but because S was declared as a student to begin with, you can only call the features that are actually available in the student class, which does not include setPR. Okay? So now in this case, if you're really sure as a programmer, so we should be smarter than the compiler. If you're so sure about it, you can do a cast. Okay? So now, again, so to judge if this line, so this one does not compile. Because the static type of S, which is students, does not have set PR feature. Again, let me emphasize again, every time I ask you about whether something will compile or not, you only look at the static type. If I ask you about output at the runtime, look at the dynamic type. Okay? Yes? Uh-huh. Good question. It's actually for polymorphic assignments, okay? So now remember, okay, let me show you that. How about we see over here? You can see over here we say Jim is assigned to RS and Jim is assigned to NRS, right? So here we are assigning Jim to be different special type, like a student, resident student or non-resident student. And we are calling the same Jim the tuition over here. So depending on which one it is pointing to, you would call the different version. So that's the use of it, right? Yeah. Okay. Okay. Guys, I'm happy. At least you're not completely lost. That's good. Okay, very good. Okay, let's talk about casting over here. So basically, the example I just talked about already said that. Okay, let's see again. Exactly the same point. Let's say we got students, we got resident students. We got resident students over here. And then, let's say we say RS is assigned to Jim. First of all, is this allowed or not? RS is assigned to Jim. No, right? You should know why. Because the static type of Jim, which is students, is not a descending class of this static type for RS, which is resident students, right? That's something you should really see. Okay? Now, however, now what I want to say, RS is assigned to set premium rates. Okay? So somehow you see the compiler is not very smart. Okay? Let me just draw some picture on this, and then I will tell you why. Okay? Let me just turn my page to there, and then I will do this on the iPad. Okay? Okay? Okay, this is what we have. We have over here, let's say static, we got Jim of type students, and we have RS of type resident students. Okay, that's static. And now let's say we do something that's dynamic. So we'll say creates resident students Jim dot make something over here. That means Jim is actually currently pointing to some RS objects. over here, right? Now, we want to do the following. We want to say RS is assigned to Jim. That's something we want to do. However, this does not compile, right? Because the static type of Jim is students. The static type of RS is RS. Students is not a descendant class of RS. That's why this does not compile. First of all, we understand that from the previous rule. But you can see that it shows that the Java compiler or IFO compiler is actually very, very inflexible. They are not very flexible. I'm trying to assign RS into some resident student object that's being pointed to by Jim, but I cannot do it. Right? That's what's happening here because of the typing rules. In this case, if you're really sure that Jim is really pointing to some object you would like to assign to, in that case, you can do a cast. Okay? How do we do a cast? Basically, for casting here, you're taking a risk. You're telling the compiler, I don't believe you. Actually, I know more than you do, so now believe me. Okay? Now, let's see how we can do that. Okay, you can go over that. And now, in general, first of all, just again, for those of you who don't understand what undecidable means, don't worry about it. If you're learning 2001, you eventually get there. Undecidable simply means something the computer cannot solve. Okay? There's no way for your compiler to know about the dynamic type for any variable. Okay? So now let's just do one more thing over here. So we got 10 minutes. That's good. So now, this is how you do cast in IFO. Actually, in your lab number 3, you will see that in one of the test cases, I do have a cast over there. So let's now learn this properly, so you wouldn't have any difficulty doing your lab. Okay? So this is how we do. I will show you also the corresponding Java code. So the concept is exactly the same. Okay? So here, think about this. First of all, you can see the, let me just use another slide. Okay? It's kind of clearer. Let's try to read this together. So we have a check. Remember, we did some, whenever we do some test feature, we got check, right? Check is certainly actually some assertion that we check at the runtime. So we say that attached, you can think of attached as instance of in Java. We are trying to say, is Jim currently attached to a resident student's objects? It's basically equivalent to say, is Jim instance of resident students? Basically the same. We're asking if Jim's dynamic type is currently resident students. We can only check that at the runtime. If it is, we are going to cast Jim into another variable called rsJim. And then we can assign this particular cast version of Jim into rs, and then we can do the rest. What if Jim is not an instance of resident students? In this case, in Java, of course, if you try to do the cast without checking instance of, you will run into the class cast exception. Okay? In IFO, they allow you to do this syntax over here to say, you better be very sure. Otherwise, if Jim happens to be not instance of resident students, you'll run into assertion violation at the runtime. Okay? You can read through the description over here. Okay? Now, I just want to show you it is equivalent to the following Java code. We say that Jim instance of resident students, if that's the case, we're going to declare this particular variable here to be cast, and we do the cast. Otherwise, if it is not an instance of, throw the exception. Okay? That's the equivalent in Java. That's pretty much what you do in Java. Okay. Guys, any questions? Yes?
When you were doing the assignment like Jim,
Yeah.
to RS,
Yeah.
right?
Yeah.
And you cannot call the methods that are referred to RS.
Uh-huh. You cannot.
Right, so what do you do when we assign RS Jim?
Why do we assign RS to Jim? Oh,
Why do we assign Jim to RS if we can't even call its methods? Methods from RS.
okay, so if I understand it correctly, so you're saying, okay. So you're saying that since we can, actually that's exactly the point we do casting, right? Because you're trying to assign Jin into RS. So first of all, you cannot do that, right?
No, not that.
Not that. Okay.
So the other way around.
Okay, sure. Okay, how about I do that on the iPad? Okay, how about that? Okay, it's good that you ask question. That's good. So we got Jim. First of all, let's double check. Okay, Jim is students, right? RS is resident students. Okay, we know that if we say Jim is assigned to RS, yes, you can do that. No, you cannot do that. Well, actually, you know, in this case over here, okay, let me just draw again the hierarchy over here. Okay, I see what the question is. Students, resident student, and non-resident students. The question was, we know that this is valid, first of all, but we cannot say Jim dot set premium rates. We cannot say that, right? So the question was, if we could not do this, why do we bother to have maybe even a student class? Why not every class is simply resident students? You're actually going back to the very design principle, the very design decision we had. Remember what we started with? We started with, in the first slide, we started with the design with this no inheritance. So students, resident students, and non-resident students. In that kind of design, you got actually 3 classes that have nothing to do with each other. You don't have any superclass, you don't have descending classes, right? But for code reuse, we actually have the hierarchy over there. So what you have is, you have this hierarchy here. This is the more general type than the other 2. And you can only define something that's common to all the students. So I tell you what, because not necessarily all the students have premium rates. Agree? Only the resident students have the premium rates. So now, if you actually don't like Jim cannot cause setup premium rates, then you should have declared Jim as resident student in the first place. But sometimes you may want to have some more general notion of students. In that case, the student can either be at the runtime some resident student and sometimes non-resident students. You know what? I'll try to think about a better response to your question. How about next time? Let me think a little bit more through to get to you. But I do see your question here. It's something to do with design choices. Yeah, you first. Yeah.
Can you cast an ancestor to descendant if the descendant redefines one of the features?
You can certainly cast ancestor to descendant if, given that the dynamic type is really matching, you can do that.
Even if the feature is redefined?
Yeah, that's fine. Yeah, question.
How about if student is an abstract class? Would everything change or is it still?
The question was, what if the student class was deferred, which is abstract? That's what you meant. There's only one thing that will change, only one thing. Every rule still apply. The only thing that changes is like this. You cannot say something like this anymore. Let's say if I say S of type students, let's say student is simply deferred. I put a star over here. You cannot do this line anymore. It's no longer possible because now student, because that's deferred or abstract, it cannot be the dynamic type. It's pretty much like in Java, right? Yeah. Yeah.
Just going back to the question that
Uh-huh.
however, will we get used sets
Mm-hmm. Uh-huh. So you mean, okay, you're talking about assign, you mean to do RS is assigned to S? This one we cannot do.
Yeah, this one we cannot do.
Mm-hmm. But for Jim is assigned to RS, yes, we can do. Yes, we can certainly, yeah, we can, yeah, exactly. So after you say Jim is assigned to RS, we know that certainly we can call Jim the tuition because Jim's static type is students, which has tuition. But now, which version is it going to call? It depends on the dynamic type of Jim. Yeah, yeah, yes. Yeah, I'll try to think a little bit better explanation to your question there to see why we really need this, because in some cases we simply cannot do the kind of assignment, right? Okay, I'll try. Yeah, go ahead.
We can follow on the same point.
Yeah.
You said you can't access ZPR, but tuition, which is an attribute
Of students.
of students,
Yeah.
will still be calculated with ZPR, with the value you set with ZPR?
Yes, that's correct. Because the dynamic binding. Because what Jim is actually pointing to is not a student object, it's actually resident student objects, right? But you cannot call S the PR. That's the tricky part, right? Okay, yes. Yep, of course. Okay, let's handle questions, and then I wouldn't go any more slides, but let's handle questions, okay? You mean this one here? Yes, go ahead. Back a little bit. Guys, please, we're not done yet, okay? Yeah. This one? You mean further or? Oh, cast. Okay.
So here you make RS div and its new variable, and you assign that to Jim. And then you assign RS to that.
So this, okay, over here, Jim was declared of static type students, right? So now, but Jim is actually pointing to a resident students class. So what we want to do is create some resident students objects on the fly at the runtime. And in order to do this, we've got to do a cast.
Right.
Yeah.
So why does iPhone make this? Like, are you making a variable necessarily away from memory? Because it's already pointing to a resident student.
Well, in this case, over here, I'm showing you only one syntax where you can have some convenience of having some intermediate variable, but there's certainly something you can do. I'll try to show you another syntax maybe next time that will show you don't have to do any intermediate variable. Okay? Okay, guys, this is what I need you to do before next Monday. Okay? I'm pretty sure in lab test 2, I'm going to ask you conceptual question about these. Okay? But I will give you certainly preparation exercise to know exactly what I expect. But before Monday, go over everything up to now. And then we'll finish the rest not very quickly, maybe in about 1 hour next time. Okay? If you got a question about lab number 3, you can come to my office hour tomorrow.